Every image is a new discovery, and each will give humanity a view of the universe that we've never seen before.
A recent announcement from a Nobel Prize-winning physicist has captivated the scientific community and ignited a whirlwind of speculation and wonder. The James Webb Space Telescope JWST, already hailed as the most advanced observatory ever launched into space, has detected something extraordinarily unexpected, something so peculiar that it has prompted a stern warning from one of the most respected minds in modern physics. The discovery stems from a distant region of the cosmos, where the telescope has captured light patterns and structural anomalies that defy the conventional models of cosmic evolution. The implications are staggering, suggesting that our understanding of the universe, its age, structure, and even its fundamental laws may be incomplete or perhaps fundamentally flawed. Before we start, smash the like and subscribe buttons for more updates. The event unfolded during a deep field observation session aimed at exploring some of the earliest galaxies formed after the Big Bang. As the JWST peered further into space, and therefore further back in time, it recorded the light from ancient galaxies at distances so great that the light had been traveling for over 13 billion years. This wasn't unexpected. The telescope had been designed precisely for this kind of observational depth. What was shocking, however, was what the light revealed. Galaxies observed at these extreme distances appeared to be far more mature, structured, and massive than any existing cosmological model would predict for that era of the universe. Instead of amorphous, slowly forming protogalactic clouds, the telescope detected fully formed spiral and elliptical galaxies, structures thought to take billions of years to emerge. What made this even more bewildering was that these galaxies exhibited redshifts indicative of a time frame barely 300 to 400 million years after the Big Bang. According to the standard lambda CDM cosmological model, such complex structures simply shouldn't exist that early. The timeline for galaxy formation has always been one of incremental growth, gradual clumping of dark matter, the condensation of baryonic matter, the ignition of the first stars, and eventually the aggregation into larger galactic systems. JWST's images, rich in resolution and detail, appeared to shortcut that entire evolutionary timeline. The data suggested an accelerated cosmic maturation, something that threw theoretical physicists into disarray. The Nobel-winning physicist who issued the warning has long been known for their work on quantum cosmology and gravitational frameworks. Their concern wasn't just about a mismatch in galactic age or structure. It was about what this meant for the foundation of modern physics. If galaxies formed that quickly, it could suggest either a revision of the timeline of the universe's expansion or an entirely new set of physical processes at work in the early universe. This includes possibilities such as variations in the speed of light over cosmic time, unknown properties of dark matter, or even exotic forms of energy that could have catalyzed rapid structural evolution. One of the more startling possibilities raised was the idea that the inflationary epoch, the extremely brief period of rapid expansion right after the Big Bang, may have included phases or properties not yet considered in current models. It is possible that quantum fields active during this time may have left imprints that accelerated matter organization in specific regions of the universe. This could create pockets of accelerated structure formation, leading to the early emergence of galaxies. Alternatively, some physicists have proposed that what JWST is observing might not even be traditional galaxies at all, but rather some unknown form of luminous structure, governed by physics we have yet to understand. Adding further mystery to the findings, the telescope also detected anomalies in the distribution of cosmic microwave background radiation in these regions, hinting at localized energy fluctuations far beyond what standard inflationary models predict. These fluctuations could be relics of ancient phase transitions in the vacuum state of the universe, events that would rewrite the narrative of cosmic origin and expansion. If such anomalies are confirmed, it could mean that the early universe underwent processes akin to phase transitions in materials, sudden radical changes in structure or state that completely alter properties in an instant. Other researchers examining the data have found unusually high metallicity in some of the early galaxies. Metals in astronomical terms are elements heavier than hydrogen and helium, typically formed in the hearts of stars and spread through supernovae. High metallicity implies not only star formation, but multiple generations of stars having lived and died within a few 100 million years of the universe's inception. Such a rapid stellar life cycle contradicts the assumed pace of early cosmic development and suggests either an unknown star formation mechanism or an entirely different life cycle framework. The potential implications stretch into the domain of quantum mechanics and relativity, raising the prospect that there may be undiscovered interactions between the quantum vacuum and gravity. One proposed avenue is that the vacuum of space isn't empty but teeming with energetic fluctuations that, under certain conditions, could foster rapid matter aggregation. If these fluctuations were more active or differently structured in the early universe, it might explain how complex galaxies could emerge so soon after the Big Bang. This observation has also reignited debate around the multiverse hypothesis. Some theorists now speculate that what JWST is capturing could be residual influence from neighboring universes, cosmic siblings whose proximity or gravitational pull subtly shape the development of our own. While purely theoretical, the alignment of unexpected galaxy formation with regions of gravitational anomaly gives a curious weight to this idea. If true, it would suggest that the cosmos is not a singular, isolated entity, but part of a larger multiversal structure, interconnected in ways that subtly imprint on observable reality. Furthermore, the warning issued by the Nobel laureate emphasized not only the observational oddity, but the deeper philosophical conundrum it presents. Science builds upon predictive models, and when the predictions fail this spectacularly, it suggests either flawed data or flawed theory. Given the integrity of JWST's design and calibration, the error is unlikely to be instrumental. The implication, then, is that our cosmological model, what we believe about the age, growth, and nature of the universe, is in desperate need of reevaluation. This isn't a minor tweak, it's a tectonic shift in foundational understanding. Another fascinating aspect of the discovery involves the arrangement of these early galaxies. They aren't distributed randomly, as one might expect from early cosmic turbulence, but instead show signs of alignment and clustering. Large-scale structure formation, what gives rise to galactic filaments and voids, was thought to emerge over billions of years through gravitational interactions. To see hints of such organization this early on suggests that cosmic architecture may have been seeded by unknown mechanisms, perhaps guided by primordial gravitational waves or anisotropies in spacetime itself. There's also the question of dark matter and dark energy. These enigmatic components, which collectively make up about 95% of the universe, remain among the most elusive concepts in science. If early galaxies formed quickly and with such complexity, it could imply that dark matter behaved differently in the early universe, perhaps more interactively or dynamically. Some physicists suggest that dark matter may have had a warm phase early on, faster-moving particles capable of triggering rapid structure formation before cooling into its current inert form. Similarly, the role of dark energy, typically associated with the accelerated expansion of the universe, is now under scrutiny. If early dark energy fields fluctuated more wildly, or exhibited different properties than today, they might have catalyzed pockets of rapid expansion and matter coalescence. This would mean the very fabric of spacetime experienced different rules in its infancy, perhaps shaped by early universe symmetry breaking or scalar field interactions beyond the standard model of particle physics. Beyond physical science, this discovery challenges the very narrative of time. Time in cosmology isn't merely a sequence of moments, but a dimension intertwined with space. If structural complexity appeared early, time itself may have unfolded differently across regions of the cosmos. There are speculative models suggesting time might flow at different rates in different areas of spacetime, depending on gravitational density and energy distribution. JWST's findings could offer the first empirical hints at these time deformation effects, providing new ground for relativistic physics to explore. Even more provocative is the suggestion that what we're observing might not be evidence of a faster cosmic evolution, but instead of a universe far older than previously estimated. If redshift interpretations are skewed by unknown gravitational or quantum effects, then these ancient-looking galaxies might not be young structures seen from afar, but older ones distorted by our misunderstanding of how light travels through expanding space. This would rewrite not only the birth date of the universe, but also its entire evolutionary arc. The role of light, fundamental to all astronomical observation, is also being questioned. Traditionally, light from distant objects is redshifted due to the expansion of the universe. However, if there are unrecognized influences on photon behavior, such as interactions with unknown quantum fields or even hypothetical particles like axions, then our interpretation of cosmic distance and age may be off base. It opens the door to a radical reconsideration of how electromagnetic radiation navigates the cosmos and what it really tells us about origin and distance. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on what James Webb really found out there? We want to hear from you. Thank you for watching, and see you next time.